this video, I'm going to discuss how to find all possible functions given its derivative. So what this stems from is the mean value theorem. And so the idea behind this is that if we know that a function's derivative is equal to 0, well, there are multiple possible functions for that. It could have been our function was maybe 2. It could have been maybe that it was a constant value 3. But the key is it is some constant value, where c is just some real number. The derivative of any constant is equal to 0. So if we're going backwards, if we're undoing this derivative, we have to get to some value that's just a constant. I almost slipped there. I almost called this an antiderivative, and that is the idea that we are approaching. The first thing I want to do, the first section here, I don't want to call it an antiderivative. I'm going to do my best to stay away from that terminology, and then eventually we'll take antiderivatives into integrals. So we're going to get more formal in how we discuss these things. But for right now, we're just going through this idea of what happens when I undo this function. Now, what this means is that anytime we're undoing a derivative, so for instance, if I had the derivative of 2x, and I want to figure out what the function looked like there, well, we want to undo this process in our heads. We want to say, well, how did I get to this 2x? We know with polynomial functions, we always count that exponent down by 1, or we always subtract 1 from that exponent. So I'm going to do the exact opposite. I'm going to say, hey, in order to have this x here, I had to have started with an x squared. Notice I completely ignore that coefficient. That coefficient I'm going to think about now. Now that I know what the variable is, I'm going to do this derivative in my head. I'm going to say, well, what would be the derivative of x squared? It would be a 2x. And notice that's exactly what we had. So this is the correct function that would get us to this derivative, but this is not the only function. Because what we just discussed a second ago, what if I had had instead a 2x plus 5? Well, that 5, the derivative is just 0, so that would be also true. What if I had had an x squared plus 103? Well, it's going to be the same derivative. All of these functions, regardless of what the constant is, will get me to that same derivative. So if I want to find all possible functions with the given derivative, I have to include this plus c, where this c is just some real number. So that would be the function, in fact, all the functions that would give me this derivative. Let's build on that a little bit. Let's say we have f prime of x equal to, make it a 5x squared minus 2x plus 3. So just a little bit more going on with this one, but I'm going to approach it much the same way. I'm going to start with that 5x squared, and I'm going to say, well, what do I have to start with in order to get down to an x squared after I took a derivative? Had to have been an x cubed. What does that mean the coefficient has to be? What does my coefficient need to be here? Well, if I took the derivative of this right now, it would be 3x squared. We wanted a 5. So what that tells me is I have to multiply that 3 by 1/3 to get the 3's to cancel. And I also need a 5 in the numerator to have that cancel and be left, or when the 3's cancel, have the 5 be left. Right now, if we were to take the derivative of this, we'd multiply the 3 down. We'd have 5/3 times 3, which gives me 5, and then the x would now be squared, so that looks good. The 2x we did just a second ago, it was x squared, but because we had the negative 2x, it has to be a negative 2x squared. And I've also added this 3 here. Where did the 3 come from? That had to have come from the constant linear function of just 3x. So the 3 derivative of 3x, and then once again I need that plus c, where c, and I should really define that c every single time, that c is just some real number. C is an element of the real numbers. And that is not my derivative, that is my function. I don't want to put a prime on that. That is my function f of x based on that derivative. So there are rules to approaching these, and when we get to the antiderivative section, we're going to have those more formal rules, but I will never really reference those. So the rules with polynomials is you count up by 1 on the exponent, then whatever that exponent is, that new exponent, you divide the original coefficient by that. I don't want to learn a bunch of new rules because I already have all the rules I need. If I know how derivatives work, I will be able to calculate these things. Let's take another one. So we've done polynomials, but what if I had, this time, sine of x? Well, let's think about what derivative gives me a sine. That would be cosine. But let's make sure that's right. I always say, it doesn't matter, if we're calling these things, antiderivatives or integrals down the road, I always say you all are very good at finding derivatives. And this is true until Calc 3. Very good at finding derivatives. Integrals are always more challenging. And so check yourself. Once we think that we have that undoing process correct, I'm going to take the derivative of this. What is the derivative of cosine? It's a negative sign. It's not sine. So in order to fix that negative, I'm going to put a negative out front. And just like that, I've fixed my problem. We are just starting to get into these, so we're not going to see very advanced versions of this undoing process. We should be familiar with our basic rules, or our basic power rules, or basic rules of exponentials. So for instance, if I had, let me call this one something different, h prime of x equal to a 3 to the x, I should be able to undo this as well. We're not going to get into the products and chain rules and quotient rules. Those are much more advanced. We will get there, just we're very early days. We're just taking the very basic rules. So our rules for exponentials, we know, we always just keep the exponential the same, but then if I were to take the derivative of this, I would have the 3x times 3 to the x times the natural log of the base of the 3. Well, we're missing that times natural log of 3, so what I'm going to do is I'm going to multiply by 1 over the natural log of 3, and that is just a constant multiple. And so now if I were to take this derivative, I'd have 3 to the x, but then I'd have the times natural log of 3 times the constant multiple, and so we do have the correct answer. But I do need that plus c because we are listing all the functions where this is true. Again, these c's are just real numbers. So we should be comfortable with all the basic rules. We're not combining rules, so we're not looking at product, quotient, or chain rules, so we won't need to worry about those. At least not very detailed. I shouldn't say there's not going to be a single chain rule because there's some very basic chain rules we could probably handle all right. So for instance, if I had e to the 5x, I think we can all figure this one out. F of x would be equal to e to the 5x because that always stays the same. But then again, just like with the last one, we need that multiple, that constant multiple to cancel out with our chain rule. We know it's just a basic chain rule. It's just the times 5. So we put a 1/5 in front. And c is just some real number. So we always have this c here until we know something about that original function. The problem with all the problems we've done so far, I don't know anything about the original function. So when I undo it, I don't know if there was a constant there that I had to put that plus c in front. But what if we're given a little bit more information? Find f of x if f prime of x is equal to 2x plus 3 and f of 1 is equal to 4. Let's see what we can do with this. So I'm going to start off the same way. I'm going to say, well, if I know f prime of x, I can find f of x. I'm going to undo the 2x. That's going to have to be an x squared because we always have to step those exponents up by 1. And then taking the derivative x squared would be 2x. That looks good. The 3, that had to start as a 3x. And then I need a plus c. Here's where we're going to do an extra step. I now have a little bit more information here. I know that my function is equal to 4 when my x value is equal to 1. So if I simplify this, I'd have 4 plus c on the right hand side. It's equal to 4. So obviously solving for my c, that means my c is equal to 0. So my function is equal to x squared plus 3x. Notice I get to leave off the c because we know exactly what it is. We're told that information. We know exactly where it started. Let's do another one. Find g of x given g prime of x is equal to secant squared of x and g of pi over 4 is equal to 1. All right, so this time I have to undo the secant squared. And when I take the derivative, do I get the secant squared? That would be tangent x. The derivative of tangent x is equal to secant squared. But I don't know what my constant is yet, so I'm going to put that plus c. Now I'm going to put in my extra information. So 1 is equal to tangent pi over 4 plus c. So when we take the tangent of pi over 4, we just get 1, and then solving for c, we get c to be equal to 0 once again. So our tangent function, our function is just tangent x. We have a 0 as a plus c again. Not all c is going to be 0, of course. Let's do one where maybe it's not equal to 0. So let's find h of x given h prime of x is equal to 3 plus, let's do e to the x, and h of 1 is equal to 4. Right, so let's start by looking the general function. So what is with that plus c? So the undoing the derivative of 3, that would have to be a 3x. Then e to the x we always know is just e to the x. But here, I haven't plugged in that initial condition yet. This is my initial condition. I haven't plugged that in, so I don't know what that c is supposed to be. I'm going to plug the 4 in for my h of x. I'm going to plug the 1 in for my x. And so now if I want to solve this thing for c, I have to subtract the 3 over. I also have to subtract the e over. 4 minus 3 is 1. And then subtracting the e as well. My c is kind of ugly, right? It's 1 minus e. It's not just a nice, pretty single number this time, but that's fine. That's really a pretty easy number to use as well. So my h of x is equal to 3x plus e to the x plus 1 minus e, because that was my c. So there's my h function. Let's find the displacement. Given a velocity of 3x plus 1 and the position at 1 is equal to 4. And I want to find that displacement between t is equal to 0 and t is equal to 2. All right, so the first thing we need to do is we need to come up with a position equation. If we want to find the displacement, we have to find s of 2 minus s of 0. So I need that position equation, so that means we're going to have to do undo the derivative. So if we see that 3x, it had to have started as an x squared, and then we're going to divide that 3 by the 2, or think about what would we have to have had to get a 3 if we're multiplying that 2 down. Well, it has to be 3 halves. And then the antiderivative of the 1, I did it again, but the undoing of the 1 would just be an x, but then of course there's a plus c there because we don't know what it should be until we can solve those initial conditions. So I'm going to plug in the 1 and the 4. So 4 is equal to 3 halves times 1 plus c. And so we get a 3 halves plus 1, that would be a 5 halves. Subtracting that over, 4 is 8 halves, so we get a 3 halves is equal to our c. So our position equation, s of t is equal to 3 halves x squared plus x plus 3 halves. And so just like we've done many times now, we have found the equation that would give us the derivative indicated with the given condition. So if we were to plug in that 1, we would know we get 4 because we just solved that. We want to know the displacement between 0 and 2. So I'm going to plug in my 0, I'm going to plug in my 2. Obviously, if we plug in the 0, we just get the 3 halves. Plug in the 2, we get 3 halves times 4. I'll do a little simplification as I work through it, plus the 3 halves. So 2 goes into 4 twice, so we get 6 plus 2 plus 3 halves. So that'd be 8 or 16 halves plus 3 halves, it's 19 halves. And so displacement, remember, we have to take where we start, where we finish minus where we start. Displacement. So it's going to be the 19 halves minus the 3 halves, which is 16 halves, for a total of 8 units. And I didn't give you any units here, so we just have to be careful that we want to make sure we're using the correct unit there. And that would be our answer, right? We're done. 8 meters, 8 feet, whatever. Let me change it up ever so slightly. So this time, instead of using this initial condition, let's do the same problem, but I'm going to use s of 1 is equal to 6. So if we think about the process, we're going to have the same initial function with the 3/2 x squared plus x plus c. That's not going to change because the only thing I changed was the initial condition. This time I'm going to plug in a 1 and a 6. So 6 is equal to 3/2. I'm going to have a 1 here, squared, plus 1 plus c. So 6 is equal to 3/2 plus 1 plus c, and so we can simplify that. That is 5/2 once again. So this time we're getting a different c value. The c, 6 is 12/2 minus 5/2 would be 7/2 plus the c. So now I'm going to come back over here to this equation that we created just a second ago, but I'm going to plug in 7/2 this time. It's an x, not a t. Because the 7/2 was the c we found just a second ago. It shouldn't be a plus c, that should just be c is equal to 7/2. And so I'm going to plug in the same 0 and 2 like we did just a second ago. 0, I get 7/2. 2, I'm going to have 3/2 times 4 plus 2 plus 7/2. And so we get 6 plus 2 plus 7/2. And that would be 8 plus 7/2, or 16 plus 7/2, which is 23/2. And so if we want displacement, we are going to have the 23/2 minus the 7/2. And so 23 minus 7 is 16/2, which once again we get 8. It's kind of interesting. That's the same thing we got just a second ago. That would be kind of a weird coincidence, especially when I'm just choosing kind of random numbers here. I just chose random 1 and 6. Maybe we figured out what's happening already, but let's test it one more time. But this time, by testing complete generality, I'm going to say s of 1 is equal to c, meaning I'm not even going to assign it that value. So we know this initial equation is going to be the same, but this time when I plug in, let me not call it c, let me use a different letter since I already used c's. Let me call it d, representing just again some letter that I don't want to assign yet. So s of 1 is equal to d, so when I plug in that 1, I'm going to get d this time. So we'll have d is equal to 3/2, that's 1 squared plus 1 plus c. And so that means our c, all we've done here is we've just made it a little bit messier, honestly. We have a d minus 3/2 plus 1, got to subtract that over as well too. Just subtracting the 3/2 over, subtracting the 1 over. So c is equal to d minus 5/2. And so I'm going to set up my equation with that d minus 5/2. So s of t is equal to 3/2 x squared plus x. And then here the c we've just found to be d minus 3/2 minus 1, which we said, I've lost it, d minus 5/2. And so when I plug in my 0, I'm just going to get that constant value of d minus 5/2. S of 2, we're going to have the same 6 in front. We're going to have the same 2, but then we're going to have the d minus 5/2. And so when we go to find the displacement, we're going to have 6 plus 2 plus d minus 5/2 minus the d minus 5/2. So this time I'm not going to just add it all together because I really can't. The d's make it hard just to kind of add from left to right, but what I do notice is the d minus 5/2 cancels in both cases. I'm left with 6 plus 2, I'm left with 8. So what we've just seen is when we do this problem in complete generality, when we just assign our initial condition to be something fixed but still unknown, we end up at that same 8. If we think about why that is occurring, the c value, let me circle those c's are the same in both the initial and the final position, so they're canceling off. Is that to say that c is never important? Absolutely not. The question I asked here was, what is the displacement? And I did that over distance. because there is it will matter. There is going to be a difference in whether that c makes a difference. If we think about having a speed, right? We know the speed that we're traveling along a line. If I start here and finish here, right? And I know the speed over that time, that speed is going to give me a certain distance covered, call it d. If I had instead said, well, let's instead start here and finish here, if we're traveling the same speed over the same interval of time, it's the same interval of time in all cases, that is the same distance d. Now, what if I had instead said, what is the position at time 3? Well, now that matters. Now that plus c matters. It matters where I start, because if I'm starting here, obviously I'm going to add a different position than if I start here. That initial condition, that given information, is going to affect where I finish. Then the question becomes, when do we need to write that plus c? We always should write that plus c until we convince ourselves that it's not going to matter inside the problem. So if we're looking at something like displacement or total distance traveled, that c is not going to really make a difference. Versus if I care about where I am at a given point, that is with the position equations, then it matters, right? But if we're looking at other examples, if we're looking at something like a marginal cost to a cost, it absolutely matters how much I invested in the company initially, or how much I put into the operation initially. So there are plenty of cases where I do care about that initial position. So as a general rule of thumb, we always want to write that plus c there when we're going from a derivative to an integral. Now we're going to see cases, like with our displacement here, where it might not matter. But it's still a good idea to write that plus c there until we decide that it really doesn't affect the problem, as we did in this last case here.